This is chapter 15, lesson 2, and here we'll talk a little bit more about equilibrium. This chapter is all about equilibrium. We've introduced the equilibrium constant last lesson, and here we're going to do some manipulations, some math with it. This chapter and the subsequent chapters will be heavier in math because of this equilibrium constant. So first of all, we're going to talk about how you can change how equilibrium constant is related to the manipulation of the chemical equation. So here it says if you want to reverse the reaction, so take a look here, we have N2O4 becoming NO2 as we saw at the beginning of the last lesson. If we flip this around, if we make NO2 our reactant and then N2O4 our product, well, how does Kc change? Well, we've just swapped reactants and products. Remember that products went in the numerator and reactants in the denominator, so effectively we'll be flipping these. And as we flipped it, essentially your constant just gets inverted. So instead of 0.212, you do 1 over 0.212. So it's the reciprocal for the reverse reaction. And then when you calculate it, you get yourself a value. A new value is the idea. So if you decide to flip a reaction around, you would reciprocate, invert your constant, your numerical constant. How about if we do something to the coefficients? So here we ask if you double the coefficients or if you halve the coefficients. So what you'll see, recall that coefficients go into the power. So this coefficient went into the power. So what you're doing effectively is you're changing the powers of your coefficient. So whatever you do to the whole reaction, if you want to multiply the whole reaction by 2, this would mean that you would have to multiply the whole equilibrium constant. Not multiply, but square the whole equilibrium constant, because the coefficients are reflected in the power. Whatever you do to the coefficients, you end up doing to the power of your constant. So how about a little example of this? We have an equilibrium system along with its constant. And the question is, what is the equilibrium constant for the reverse reaction? What we mean here then is we're going to flip around the products and the reactants. So our K originally was products over reactants. Now we're flipping it, so these two get inverted, which means our constant gets inverted. So because Kc in this case is 2.4 times 10 to the negative third, to get the new Kc, we'll simply invert it. So 1 over that, 2.4 times 10 to the negative third. If you put that into your calculator, you should come out with a value that looks something like 417, and really 420, following significant figure rules. So 420 is our new Kc. And recall, Kc won't have units. Here it says, what is the equilibrium constant for the reverse reaction if the coefficients are halved? So now what we're doing is we're cutting the coefficients in half. And remember, whatever we do gets reflected in the power, because the coefficients went into the power of our equilibrium constant. So now what we're doing is we're taking our equilibrium constant and raising it to the power of whatever we did. In this case, we halved it. So we raised 420 to the half power, and if you recall from mathematics, raising something to the half power is equivalent, it's the same thing as taking the square root of it. So really we're taking the square root of this value. And so take the square root of 420 roughly, and you get roughly 20. So the equilibrium constant comes down to 20. And hopefully this little example solidifies the idea. We're going to talk about something called heterogeneous equilibrium. This is equilibrium, this refers to reactions which have different states in them, both liquids and solids and gases and aqueous solutions, and how we deal with equilibrium in that case. So here it says the concentrations of solids and liquids are essentially constant. And this is kind of a general way of explaining it. There is a more sophisticated way which we'll lay off for now. Here it says because solids and liquids don't change in their concentration. For example, if you want to think about this a little bit, what if I have a certain amount of a substance. I have a certain number of moles of this substance, and I have a certain number of liters of this substance, and of the liquid. So if I were to cut this in half, now I have less mole of this substance, but I have proportionately less liters of the substance. So my ratio of N over L stays the same for a solid or a liquid. And not so with gases. Gases can be compressed and decompressed. So maybe this allows us to see why liquids and solids stay constant. And we will not put them, they do not appear then in the equilibrium expression. It's as easy as that. So for example, the equilibrium expression here would be just your two aqueous concentrations. We exclude the solid. We do not put it. Technically it would be on the bottom here, but because it's a solid, its concentration doesn't change, we don't include it. Because if its concentration doesn't change, dividing by 1 won't really do much. And another example of this, this is kind of a visual reaction example. We have calcium carbonate as our solid. Here we have it in the right little beaker. And what happens is that calcium carbonate produces CO2 gas along with some calcium oxide solid. And here visually we're showing you that it doesn't matter if you have a lot of calcium carbonate, a little bit of calcium carbonate and a lot of calcium oxide, or a little bit of calcium oxide, a lot of calcium carbonate. The amount of gas above is equal. So it does not matter that we change the amount of solid. Hopefully this helps to see the same concept. So why don't we practice writing these heterogeneous equilibria for a few of these. Here it says write both the Kc and Kp for each one of these. So Kc, remember, is defined in terms of concentration, and it's still products over reactants. So in our case we have a liquid for one of our products, so this liquid will not appear in the equilibrium expression, but gases will appear. So CO, the concentration of CO goes on top, and the concentration of both of these are gases, so we will include these. The concentration of CO2 times the concentration of H2. That would be Kc. And likewise, if we were to define Kp, we'd have to get the pressures of these, but the definition would essentially be the same. It would be the pressure of CO divided by the pressure of CO2 multiplied by the pressure of H2. Remember, numerically these two will be different, but they're set up the same way, because concentration does not equal pressure in most cases. For this one, we can do the same thing. Kc, for this part B, will exclude the solid, and will exclude this solid. So really, we're down to our gases. So let's take the concentration of CO2. In this case, don't forget about the coefficient. We'll have to square it, divided by the concentration of CO, our reactant, likewise squared. And Kp would be defined the same way as the pressure of CO2, and then we'll have to put the whole quantity squared, divided by the pressure of carbon monoxide, whole quantity squared. And that one ran away a little bit. So this would be Kp. So the lesson here is we exclude liquids and solids. Gases and aqueous we keep. Now we're going to finish with a little bit of calculations. Now we're going to, in this lesson we'll do simple calculations, and in the following lessons we'll do some tough, challenging calculations in honor of the Olympics. So here is, we're going to utilize K, the equilibrium constant, to do some calculations. We'll do two of them here. This first one says a mixture of hydrogen and nitrogen in a reaction vessel is allowed to attain equilibrium at a certain temperature. The equilibrium mixture was analyzed and found to contain these molarities. And from this we want to calculate Kc for this reaction. So this will be simply setting up Kc and then plugging the values into them. So we'll do this on the next page. So what we've got, based on the balanced equation, our equation again is N2 plus plus 3 hydrogen in equilibrium with 2NH3. So setting up the constant Kc, again we have products divided by reactants, so Kc will equal concentration of NH3 as our product squared over the concentration of N2 times H2 squared, cubed in this case. Let's go and plug the values in. So in our case, the concentration of NH3 was found to be 0.00272. We'll have to square this quantity. And then on the bottom, N2 was found to be 0.0402. H2 was found to be 0.1207. And then we'll have to cube this quantity. Oftentimes I recommend calculating these out separately and then dividing them because it's possible to plug these in incorrectly into the calculator. So I would recommend calculating the top and the bottom out separately. So calculating the top out, squaring that value gives us a tiny number, gives us 5 zeros and 7398. And then doing the same thing to the bottom, let's go ahead and multiply both of these together. So we got ourselves 0.1207 cubed multiplied by 0.0402. We also have a pretty tiny number at the bottom, 407069. And then finally dividing these two together. Go ahead and put this into your calculator, see if you agree. That we get ourselves a value of 0.1, and because we have 3 sig figs as our lowest, so we'll do 0.105. And again, no units. So this is the K experimentally derived. So before we defined K, and now we can actually see, and in general recall that K, since K is smaller than 1, this probably tells us that the reactants predominate. In other words, at equilibrium we have a lot of reactants and not much product, because the Kc is a small value in this case. And then we can use this value to calculate the possible future concentrations of equilibrium. Alright, let's do one more example problem. Same equation. In another experiment, we find the equilibrium partial pressure. In this case we're using Kp. So the value of Kp is different than Kc. Notice it's quite a bit different for the same system under similar conditions, because Kc does not necessarily equal Kp. So we find the partial pressures of hydrogen and nitrogen, and we're asked for the partial pressure of ammonia. So let's go ahead and do this one. Again, in the previous example we defined K. Let's go ahead and redefine K. P in this case to be the pressure of ammonia squared, this again is your product, divided by the pressure of your two reactants. So the pressure of N2 multiplied by the pressure of H2. This quantity must be cubed. So what we'll do essentially is plug and chug, plug the numbers in, and see if we can solve for the unknown. In this case the unknown would be NH3. So Kp is given as 1.45 10⁻⁵. That will equal the pressure of NH3 squared. So we can say, we can just keep it as pressure of NH3 quantity squared divided by the pressure of N2, which is given to us as 0.432, atmospheres, and the pressure of H2, which is given to us as 0.928 atmospheres. We'll have to cube this value. So what we'll have to do is move these two over to this side and then solve for NH3. So we got ourselves 0.432 multiplied by 0.928 cubed multiplied by 1.45 times 10 to the negative fifth. And this equals the pressure of an H3 quantity squared. And to solve for the squared, for NH3, we'll have to square root. So if we square root this entire side, the squared disappears. So why don't we calculate out what's in the square root, multiply those numbers out in your calculator, and then rewrite it, and we'll square root that, and we'll hopefully get a fine answer. So see if you plug that in, multiply whatever is in the root, we should get ourselves square root of a tiny number, 5 zeros, 50061. We can say to 5006 will be the pressure of NH3. So go ahead and square root that number. And we should get ourselves a pressure that is equal to, for sig figs' sake, we have 3 sig figs again. So let's go ahead and put 0.00224. In this case, we do have a unit because we're asking for pressure, and the pressure will be in atmospheres, since we were given the pressure in atmospheres for the H2 and N2. So small pressure, quite a bit small, actually, just a 2/1000ths of an atmosphere, which is really tiny pressure. But that's due to the fact that your Kp value is really small, and that would make sense. That's because if Kp is small, your product is really small, your reactant is great, and because NH3 is a product, we have a really small pressure of our products. And this concludes lesson 2 of chapter 15.